Hello viewers, welcome you all. In today's lecture, I am going to take up the next topics of nuclear physics, and the topics that I am going to discuss today, they are radioactivity and nuclear decay process, right? So in this lecture, I am going to cover up the important points of these two topics, right? And in the next lecture, I will take up the questions related to these two topics, right? So first of all, I am coming to the radioactivity. We know very well that radioactivity was discovered by French physicist Henry Becquerel in 1896, right? Henry, right? And according to the definition, the process of spontaneous emission of alpha, beta, or gamma radiation, right, from a heavy nuclei is known as radioactivity. All the nuclei with Z greater than 82, they show radioactivity phenomena. I mean, they are capable of emitting alpha, beta, and gamma rays, right? Now the question is, why the radioactivity is happening, right? We know very well, we have seen in the binding energy per nucleon graph, right? We have seen packing fraction, also we have seen nuclear stability graph. So all these points has revealed that all the nuclei in the nature want to get stable. I mean, they want to have maximum binding energy, and they can do it, right, by coming into the intermediate region. Intermediate means neither too much small, neither too much large size, right? So all the heavy nuclei, they are unstable. All the lighter nuclei, they are unstable. We have seen the graph of binding energy per nucleon. I am showing it to you once again. You can see here, right? This is I'm drawing a similar graph for understanding, right? You might have remembered that that graph was, right, of this type, right? Here A, it is mass number and it is a binding energy per nucleon. So you can see here that the nuclei of this intermediate range, they are highly stable. All the nuclei which are on this side, they want to come here, which are on this side, they also want to come here. Same is the situation for packing fraction and nuclear stability graph, right? So all the heavy, here we are talking about the heavy nuclei, right? The nuclei with Z greater than 82. So they show radioactivity. Radioactivity means emission of alpha, beta, and gamma rays. Now I am coming to all these three process one by one. So the first one is alpha decay, right? We know very well, first of all, that what is alpha particle? It is helium nucleus 2He4, combination of 2 proton plus 2 neutron, right? So when nucleus, for example, parent nucleus is represented as ZXA, it emit alpha particle, then its atomic number decrease by 2, mass number decrease by 4 plus 2He4. So this is the alpha decay. Now if I talk about the beta decay, right? Now in beta decay, we have three type of process involved: beta negative, beta positive, and electron capture, right? So the first thing is, what is beta particle? So beta particle is basically a fast moving electron or positron, antiparticle of electron. So we call them as beta particles. They are fast moving, means their speed is very high as compared to the speed of ordinary electron, and it can be comparable to the velocity of light. So we call these particles as beta particles, right? Now if I talk about the beta decay, then in beta decay, as I told you, I can have three type of process: beta negative decay. Beta negative decay means emission of electron, right? So in beta decay, if I have a ZXA, then it will give me Z minus Z plus 1 by, sorry, here it will be also by, because this nucleus now is changed, this element is now changed into another one. This is parent nucleus, it is daughter nucleus. Z plus 1 by A plus minus 1 E 0 plus anti-neutrino associated with electron. So this is the beta negative decay. Now you can see the charge conservation, I mean atomic number conservation and mass number conservation on both the sides. So this is basically a spontaneous conversion of a neutron into proton plus electron, right, plus anti-neutrino. So this is the process that takes place inside the nucleus. And why this beta negative decay occurs? Because the nucleus have excess neutrons. I will come up to this in the later part of this lecture. So this is beta negative decay. If I talk about the beta positive decay means emission of a positron. So in this case, ZXA parent nucleus, Z minus 1 by a daughter nucleus plus 1E 0 plus neutrino associated with electron, right? So you can see here, now it is positron. This is the antiparticle of electron, right? Again, charge is conserved on both the sides, mass number is conserved. You can see in both the cases there is no change in the mass number, right? And if I go into this process, then it is basically the conversion of proton into neutron plus positron plus neutrino. Right? This is the process that takes place inside the nucleus, and it takes place because the nucleus have excess protons, right? So the third process that is involved in beta decay is electron capture. In electron capture, what happens? Actually, the nucleus captures its innermost cell electron, and thereby proton convert into proton plus electron, that will give you neutron plus a neutrino associated with the electron. So this is the process that take place. I can write it in this way: ZXA plus minus 1 E 0, that will give you Z minus 1 by A plus neutrino associated with electron. So this is the process. Again, the charge is conserved, mass number is conserved on both the sides, right? And you can see this process and this process they are quite similar: beta positive decay and electron capture. But electron capture process dominate in very heavy nuclei. Why? Because in very heavy nuclei, the cells of the electron are very close to the nucleus, and it is possible that the nucleus can capture a innermost electron and converts its proton into neutron, right? The same process that happened here, right? So these are the three process by which nucleus can decay and convert itself into another nucleus, right? And it can move toward the stability, right? So these are the three main processes that are included in the radioactivity. Now I am coming to the properties of alpha, beta and gamma rays. So alpha rays properties. Alpha rays, I told you that these are basically helium nucleus, a combination of 2 proton and 2 neutron. It is represented as 2He4. If I talk about the velocity of alpha particle, then it is a 10 raised to power, approximately 10 raised to power 7 meter per second, right? We can say. Now I am discussing the properties because usually question is asked from these different particles or rays, that which one has highest ionization power, which one has highest penetration power. So if I talk about the ionization power, right, ionization power, then alpha particle has the highest ionization power. It is 100 times than beta particles and 10,000 times than gamma rays, right? It is having highest ionization power. This is because because of its size. Its size is very large as compared to beta particle and gamma rays. Gamma rays are basically electromagnetic radiations. So it has enough chances of interacting with the matter through which it passes. So that's why it produces high ionization in the material or in the medium in which it passes, right? If I talk about the range range of alpha particle, very important property. Then obviously when it will produce very high ionization, range will be small, right? So its range is very small. In all alpha, beta and gamma rays, it has the lowest range, and we can say it is a few centimeter in air, 2 to 10 centimeter in air, right? It can travel. It can be easily stopped by a plain paper even. So the range is lowest, but the ionization power is highest, right? The one more thing about this alpha rays is that it is affected by electric field and magnetic field. In both these fields, when this particle pass, it got affected. I mean, its path is changed. It means this particle is a charged particle. Only then it can got affected. So obviously it is charged because it is a combination of 2 proton and 2 neutron, right? Now I am coming to the properties of second, that is beta rays. As I told you that beta rays are basically fast moving electrons, right? So these are basically either electrons or antiparticle positrons, right? Fast moving means they can have velocity comparable to the velocity of light. I mean, they can have velocity 0.1 c to 0.99 c in this range, right? They can travel with such a high speed, right? Now, as far as the ionization power is concerned, right? Ionization power. So as I told you that their ionization power is less than alpha particle. It is 100 times less than alpha particle, but it is greater than gamma rays, right? It has intermediate ionization power, right? As far as range of this beta particle is concerned, then beta particle has high range as compared to alpha particle, right? Because they are now fastly moving, their size is small, so they can travel large distance in the medium. They can even penetrate through 1 centimeter of aluminum sheet, right? This is the range, or we can say penetration power. They have high penetration power as compared to alpha particle. I told you that alpha particle can be stopped by a simple piece of paper, but beta rays can pass through 1 centimeter of aluminum. Again, these beta particles are also affected by electric field and magnetic field, right? Because again, these are charged particles, either electron or positron, so they are affected, right? They will change their path when they will pass through the electric field or magnetic field, right? So this is about the beta particles. Now I am coming to the third one, that is gamma rays. Now, I told you that gamma rays are basically electromagnetic radiations, right? The gamma radiation or gamma decay emit from the nucleus when nucleus has excess energy. It is in the excited state. So it radiates its energy in the form of gamma ray and it comes back to the ground state, right? We know very well that gamma ray travel with electromagnetic ray travel with the speed of light. So their speed is right. As far as their ionization power is concerned, their ionization power is lowest, right? Lowest in all these three categories, alpha, beta and gamma rays. Lowest ionization power, but the range is highest. I mean, their penetration power is highest, right? They can even penetrate through a 30 centimeter thick iron sheet, right? They have such a high penetration power that they can even penetrate 30 centimeter thick iron sheet. So their penetration power is highest, their range is high. Range means the distance up to which they can travel. It is highest, but ionization power is lowest. So usually question is asked from here. So now, as far as the effect of electric field and magnetic field is concerned, they are not affected by electric and magnetic field, because we know very well they are electromagnetic radiation and they are neutral, right? So they don't have any charge, so they are not affected by electric field or a magnetic field. So this is about alpha, beta and gamma rays properties and basics about the decay of these three processes. right? Now I'm coming to the some important relations of radioactive decay. The first one is radioactive decay law. We know very well, we have learned it so many times, that according to radioactive decay law, dN upon dt, rate of change of the nuclei, is directly proportional to number of the nuclei present in the sample at that time, right? So if we simplify it, n is equal to n naught e raised to power minus lambda t. Here lambda is a disintegration constant, and its units we can calculate per second, per year, right? Per year or per mint, it can have these units, right? N is equal to n naught e raised to power minus lambda t. So if we plot a graph between the time and the number of nuclei, then we have to remember that graph. I'm plotting it here for understanding. Decay curve, we call it as a radioactive decay curve. So if we plot, then it will not touch this axis. This is n naught, initial number of nuclei in the sample, and this is the decay graph. You can see that this curve will touch this line or this axis when time will becomes infinity, right? Only then n will become equal to 0, right? This is n. So we can be asked question from here that the given material or given radioactive material nuclei will decay completely when time will become infinity. Only then they will decay completely, or I mean the left out nuclei in the material will be equal to 0. So this is the graph and this is the meaning of it. Now we know what is about the half-life period. This is also an important point of life of a radioactive substance or radioactive material. So half-life is basically the time during which half of the nuclei present in the sample decays. This is the meaning of half-life of a radioactive nuclei or radioactive sample, right? For example, suppose I have 100 gram of given material and it has half-life of 4 days. Then it means after 4 days there is chance that 50 gram of the sample will get decayed. Or we can say, if I explain it in another way, suppose I have 100 nuclei, right, and 4 days are the half-life. Then after 4 days there is a probability that 50 nuclei will decay. Now it doesn't tell us which of the 50 nuclei will decay, but there is chance that 50% of the nuclei will decay, right, in 4 days, right? Then in next 4 days the remaining 50%, right, 50 remaining 50%, 25 of the nuclei will decay. So this is the meaning of half-life. We know very well what is the formula for it. T half is equal to 0.693 upon lambda, right? Lambda is again disintegration constant. We can be asked the meaning of decay constant. So lambda is equal to 1 defined as the time. If I put here in this relation lambda is equal to 1 upon t, then I will get n is equal to n naught upon e. So we can say that disintegration constant is defined as the reciprocal of that time during which, right, during which the nuclei decay to 1 upon e time of its initial value. So it can be explained in that way, right? So this is about the half-life, right, and radioactive decay law. Then we have average life. Now what is the meaning of average life? Average life of a given sample. I told you that if I have 100 nuclei and the half-life is 4 days, right? So it means after 4 days 50 nuclei will decay. Now it doesn't tell that which 50 nuclei will tell. So it means the different nuclei present in the sample will have a different lifetime. So if we take the average of the lifetime of all the nuclei, 100 nuclei present in that sample, then it comes out to be T average is equal to 1 upon lambda. This is the relation for it. Here lambda is again disintegration constant, and I can write it in terms of half-life period. T half is equal to 0.693 into T average, because 1 upon lambda 0.63, yeah, you can see here this relation. T half is equal to 0.693 upon lambda. So 1 upon lambda is equal to this, right? This is the relation between half-life period and average life, right? Now I am coming to the units of radioactivity. So SI unit of activity is defined as the number of disintegration taking place per unit time, per second, right? This is the meaning of activity, number of disintegration or the nuclei decaying per unit time. It is A is equal to lambda into n. It is defined as this. Activity is equal to lambda into n, right? So if I write down the units, then SI unit of activity is Becquerel, and Becquerel means 1 disintegration per second, right? So this is the SI unit, right? It is named after Sir Henry Becquerel, right, who has discovered the radioactivity. Then we have another units, Curie, right? Curie is defined as 3.7 into 10 raised to power, it is largest unit, disintegration per second. Then we have another unit, Rutherford, right? Rutherford is defined as a 10 raised to power 6 disintegration per second. So these are the commonly used units in radioactivity. SI unit is Becquerel, 1 disintegration per second. Then we have Curie, 3.7 into 10 raised to power 10 disintegration per second. Then Rutherford, 10 raised to power 6 disintegration per second, right? Now I am coming to the very important part of important topic of this topic, that is radioactive series. Radioactive series. So radioactive series, if we look at all the radioactive nuclei present in the nature, then it is found that these all nuclei can be divided into 4 different series. Series means these nuclei will start from a parent nuclei and they will convert into daughter nuclei, and then that daughter nuclei will further convert into the granddaughter nuclei, right? Then that further, ultimately this process will continue. We have a stable end product, right? So starting from parent, that was the beginning, we have an end, that is stable. So why I'm taking here only 4 series? You can ask a question, why in the nature we have only 4 series? This is because alpha decay, right, it reduces the mass number by 4, right? So we can have 4 series only possible. Why? Because we can have either A is equal to 4n, A is equal to 4n plus 1, A is equal to 4n plus 2, A is equal to 4n plus 3. Now if I want to go A is equal to 4n plus 4, then again I can get this by 4n plus 4. This can be achieved by alpha decay. I mean this nuclei can come back here, right? So same thing. So that's why we are taking only 4 radioactive series in the nature, because alpha decay reduces the mass number by 4, right? So 4n mass number can be there, 4n plus 1, 4n plus 2 and 4n plus 3. If we go to 4n plus 4, again the same thing. So this is the answer to this question, why we have only 4 radioactive series in the nature. Now I am coming to the different series that I want to discuss here. So we have to remember that we have 4, this is serial number, right? 1, 2, 3, fourth series, right? Name of series, series name, right? Mass number, right? Parent, stable end product, and half-life. So if I look at this, then first series is a thorium, right? It is 4n and parent nucleus is a 90, thorium 232 and product is a 82, lead 208. Half life period is approximately, I am writing approximately 10 raised to power 10 years, right? The second one is neptunium. The mass number is 4n plus 1. It is 93, neptunium 237, right? And product is a bismuth 209. Then the half life is 10 raised to power 6 years. Then we have a uranium series 4n plus 2, it is 92, uranium 238, it is, and product 82, lead 206, right, and it is 10 raised to power 9 years. The last one is again uranium, or we can call it as actinium series, actinium 4n plus 3. We call it also as uranium series because it also starts with the uranium, but it is U235. Otherwise, it is actinium, right? The end product is 82, lead 207. It is 83 bismuth, right? And 10 raised to power 8 years. So first of all, we have to remember the name of these four radioactive series. We have four radioactive series: thorium, neptunium, uranium, and actinium, right? 4n, 4n plus 1, 4n plus 2, 4n plus 3. What is their parent and daughter nuclei? What is the half-life? Now, usually question is asked that why neptunium series do not exist in the nature, or the member of neptunium series are not observed. The reason is the half-life of this series is very small, 10 raised to power 6 years, right? We know what is the age of universe, right? Around 15 billion, 10 raised to power 9 years. 15 billion years. So this time is very large as compared to this time. This time is not comparable. So that's why Neptunium series members are not observed, right? We can say that this series members has decayed completely and they have reached at the stable end product. But these series 1, 2, 3, they are still active in the nature and we can observe them. So this is about the four radioactive series. Now, usually question is asked that if I consider, for example, thorium series, the first series, right? That starts with the 90 thorium, right? 232. So you can be asked, and this is the end product, 82 lead 208. You can be asked that tell that how many alpha particle and beta particle will be emitted in this series. So you can calculate very simply how the difference between the mass numbers first of all. So it is a 208, 230, 24. 24 mass number difference means 6 alpha particles will be emitted. Now, if 6 alpha particle will be emitted, then 6 into 2, it means 12 decrease in Z will be observed. Atomic number will be changed by 12, but here you can see 82, 90, it is changed by 8 only. So what, how this 12 and 8 can compensate? So they can compensate or they can adjust. 8 can be converted into 12 by simply how? Beta decay, right? So beta decay will either decrease or increase the atomic number. So here it will decrease, beta decay will decrease. So when beta decay will decrease, then you can say that we will have 4 beta particles, right? And beta particles are which? You can see here. You can see here that this one. You can see this electron emission decrease the atomic number. So beta negative decay, you can see here it is not sorry, beta negative decay. Yes, it is beta positive decay. It was electron capture. Beta negative decay increase the atomic number. Beta positive decay decrease the atomic number. So here you can have 4 beta positive decay. They will decrease the atomic number. So obviously you will have 4 beta positive decay, and you will have how many? Uh, 6 alpha decay. So 6 alpha decay will decrease the mass number by 6 into 4, that is 24, and it will decrease the atomic number by 6 into 2, that is 12, but we want to increase in the atomic number by 8, right? You can see 82, 8, yes, 8. So we want to it is decreased by 12, right? Decreased by 12 means 90 minus 12, it will become 78. So I want to increase, right? 78 to 80, 82, 4 increase. So 4 increase means I think it will be beta, you can see here increase, yes, it will be beta negative, right? So sorry, initially we you know assess is wrongly. So it will be beta negative decay, 4 beta negative, right? 4 beta negative, because we have already reduced the beta negative decay. 4 beta negative particles will be emitted. So when 4 are emitted, they will add plus 4. So it will give you 82. So this is the question I was talking about. How many alpha particles? We have 6 alpha particles and 4 beta negative, right? So this is the number of alpha and beta particles that emit during this series, right? In order to make this series complete, I mean starting from thorium and end at the stable product 82, lead 208. Similarly, you can be asked from all these series that calculate the number of alpha and beta particle. So the logic is same. This one, first of all, you have to look at the alpha particle, right? And then calculate the change in the mass number. Then you can take into account beta decay also, so that in beta decay the remaining mass change in that number can be adjusted, right? If I talk about the Neptunium series, right? Sorry, Neptunium series, you can see 237 and 209. It is 237 and 209. 28, right? So 28 is the change in mass number. So 28, and what is the change in atomic number? 93 and 83, 10. 28, A changes by 28 and Z changes by 10. So A changes by 8 means because A can change only by alpha decay. So we have 7 into 4, 7 alpha particle that will reduce by 28, 7 alpha particles, right? But 7 into 2, 14. So atomic number will decrease by 14, right? Now, if I want this by 10 only, then what I have to do, because it will decrease atomic number by 14, right? Alpha decay. So I want it 10, right? 10 means I want to add 4 into that, right? I can show you, it was 93, 83. Yes, 93 to 83. So 93, we have decrease of 14, right? It will make 93 minus 14. right? It will make 79. Atomic number will be reduced to 79. What here it is? What? 83, right? So we want to have a 4 beta negative particles. Only then this will be added to here, right? Then it will become a 83, right? So this is the way of doing it. 80 28 decrease in mass number. So 7 alpha particles are there. Then 7 into 4 28, right? What 7 to 2 14, so it will decrease by 14, but we want to change of 10, so it means 4 beta negative particles will also be there, right? So this is the case of Neptunium series. How many? 7 alpha particle and 4 beta negative particles, right? Similarly, you can have the number of alpha and beta particles for other two series. You can be asked and you can calculate for these two series, number of alpha particle and beta particles emitted. Right now, I am coming to the next topic, and it is range of alpha particles. So, by doing different experiment, it has been observed that the range of alpha particles, usually you can be asked a theoretical or numerical problem, range is directly proportional to e power 3 by 2. Right? This is the relation between the energy and range. Here E is the energy of the alpha particles, right? And R is the range, distance up to which this can travel. I can write it R is equal to a constant A into e power 3 by 2. Here A constant is equal to 0.318, right? So you can use this relation for calculating the range. Then we have a Geiger-Newton law. Geiger-Newton law. So it is again an important topic in nuclear physics, Geiger-Newton law. So according to this law, if I plot a graph between the logarithmic of disintegration constant with logarithm of r, right, range, right, then approximately a straight line is obtained for each radioactive series, right? And according to this Geiger-Newton law, the relation is equation is a log of lambda is equal to a log of E energy plus B constant, right? This is the relation. In terms of energy, we know energy and range are linked, so it can be written as a log of lambda is equal to a log of range plus B, because we know if I took it there, it will become E is equal to R power minus 3 by 2. So if I put it here, 3 by 2 will come here, let it is A dash. So again the same thing. So this is the equation. These two are the equations of this law, Geiger-Newton law, mathematical form, right? The relation between the logarithm of disintegration constant for the given alpha emitter, right? Alpha emitter. This is very important, right? And this is energy of the emitted alpha particle, and this is a range. So if we plot graphs between, as I told you, log of lambda and log of r, then you will get, I'm plotting it here. Two axis, log of range and log of disintegration constant lambda. So if you plot, as I told you, the graph, then you will get straight lines. First series, for second series, for third series, for fourth series, you will get these type of lines like uranium series, neptunium series, actinium. So this is the Geiger-Newton law. This is mathematical form, and meaning is that when we plot a graph between the log of lambda with log of range for a alpha emitter, right? Right? Then we get a nearly straight line, right? For each radioactive series, right? This is Geiger-Newton law. Then energy of alpha decay. This is a very, very important. Energy of emitted alpha particle. So for it we have to remember the relation, right? That we know very well when Zxa convert into Z minus 2 by A plus 4, A minus 4 plus 2He4 plus Q. Q is the Q value of the nuclear reaction, either energy absorbed or energy evolved. So if I am writing directly the result of this entire reaction when we apply the law of conservation of energy, both mass and kinetic energy, then we found that energy of the alpha particle T alpha is equal to A minus 4 divided by A into Q value of the nuclear reaction, this reaction. So by putting the value of A and Q, if they are given, I can calculate the value of the alpha particle kinetic energy, right? So usually question is asked from here that you will be given a situation and you will be asked to calculate the energy of the emitted alpha particle, right? So we can use this relation. Now I am coming to the decay processes in details. Decay processes. The first one was alpha decay. So in alpha decay, we know very well an alpha particle is emitted from a atomic nucleus, and this alpha particle has energy of the order of 5 to 10 mega electron volt. So usually question is asked that how alpha particle emission is possible when the nuclear potential barrier that is of the order of 25 mega electron volt. We have to remember that the nuclear potential barrier is of this order, energy of alpha particle is of this order. So how this alpha decay is possible? So the answer to this is quantum mechanical tunneling, right? It was explained with the Gamma-Taylor theory of alpha decay, right? So I'm not going into all that theory, but the thing is that alpha decay is possible because of the quantum mechanical tunneling. The potential barrier of nucleus is of this order, the energy of the alpha particle is of this order, right? And I explained you that what is alpha decay and why alpha decay is taking place. Alpha decay took place when the size of the nucleus is very large and the nuclear forces are not capable of maintaining all the nucleon inside the nucleus. We know very well the range of the nuclear forces is small. So if the size become large, the nucleus will try to reduce its size, and it is possible by alpha decay because it reduced the mass number by 4, right? The second one is beta decay, and in beta decay, beta negative decay. I told you that beta negative decay means neutron, proton plus electron plus antineutrino associated. So why this reaction takes place inside the nucleus? Because the nucleus has excess number of neutrons, and these neutrons are becoming a trouble. How? Because they are increasing the size. So nucleus want to reduce the number of neutrons, right? So it can do it by changing it into the proton, and in this process electron and neutrino is emitted, right? This is beta decay, and it is possible if I look at the masses of the parent and daughter atoms. So it is possible if mass of this parent atom is greater than the mass of Z plus 1, right? The daughter atom that is formed when ZXA changes into Z plus 1 by A plus minus 1 E0 plus, right? So if we look at this process from the perspective of law of conservation of mass energy, then it is possible only when this condition is satisfied, right? This is for beta negative decay. Similarly, if I look at beta positive decay, same thing, but we will have the relation, that is uh, it is possible only when the given relation in this case is, let me check it. So it is possible if mass of, I am writing it, mass of parent atom is greater than mass of daughter atom plus 2 times mass of electron. This is very important, that beta positive decay can take place if this condition is satisfied. You can write it in this way also, mass of parent should be greater than mass of Z minus 1 daughter plus 2 times mass of electron, right? The analog of this equation, right? Similarly, for electron capture, the third process, electron capture. For this, if we apply the law of conservation of mass energy, then it is found that it is possible if m of parent should be greater than m of daughter, Z minus 1. So in this case, we have only this relation, but for beta positive decay, this condition should be satisfied. So these are the three conditions that we have to remember, because question can be asked from here, that what is the condition for mass energy conservation for beta negative decay, beta positive decay, and electron capture. So this is all about the different topics related to the radioactivity and nuclear decay process, right? In the coming lecture, I will take up the important questions based on these topics that are asked in different competitive exams, right? So thank you very much.